Okay, this is quantums and photons. First thing we're going to do is define what a quantum and a photon is. Okay, so a quantum. All right, quantum is the minimum amount of energy that can be gained or lost by an atom. Okay, the energy of a quantum equals h frequency. Okay, where h equals Planck's constant. Okay, Planck was a guy that figured it out. So Planck's constant, and that is equal to 6.626 times 10 to the negative 34th joule seconds. Okay? And then V is frequency. Okay? Just, again, basic math. Plug in this constant for H. Use your given frequency, and you're going to have the energy of that quantum. Okay? A photon. A photon is a massless particle that carries the quantum of energy. Okay? So a quantum is carried by a photon. All right, and then energy of a photon equals, again, hv. Okay? Now, if we know that C equals wavelength times frequency, okay? If we isolate frequency here, okay, we get frequency is equal to the speed of light divided by the wavelength. Okay, so all we're going to do is take this and substitute it for the frequency and get second possible equation, right, where energy of the photon is equal to Planck's constant, which is h from up here, okay, times c over wavelength. Okay, so that's it. All right. So let's talk about a couple of different people. First guy is named Max Planck, and you could probably guess that he is the one that came up with Planck's constant. All right, he studied light that emitted, light emitted by heat. Okay, light emitted by heat from objects, obviously that had been heated up. Okay, from hot objects, and that this energy is quantized, meaning you can put a number to it. Messing up here. This energy is quantized. Okay. Matter absorbs energy in whole number multiples of this constant times the frequency. Okay. So he determined that matter absorbs energy whole number multiples of his constant, which was h, the 6.626 times 10 to the negative 34th. Okay, times the frequency. All right, so his constant makes those whole number multiples work. Okay. Second guy I want to tell you about, or that we're going to talk about, is Niels Bohr. Okay. Now, I mentioned the Bohr model of the atom when we were talking about the dead guys, but that we weren't really going to get into what his actual model was. But what he did was he developed the quantum model for the hydrogen atom. Okay. And he proposed that the hydrogen atom only had two states. He proposed the hydrogen atom had only two states, and he called those states the ground state and the excited state. Okay, so the first one is the ground state. All right. You know, this is the ground level. This is the lowest allowable amount of energy for an atom. So it's the lowest allowable energy state of an atom. And this is the first level. First level of energy. Okay, the lowest that it can have. Okay? And then he also said that the other state is called the excited state. Okay? And the excited state was when an atom gains energy. Okay, so when that atom gains energy, it doesn't matter how much energy it gains. Once it gains more than the ground state, it becomes excited. Okay? And we'll talk about more towards the end here, the difference between the excited state and the ground state. But basically, he also stated that electrons, and this is where he comes in with his Bohr model of the atom, that electrons move around the nucleus in only certain allowed circular patterns, okay, or circular motions. And only okay, now this was later proven incorrect. Okay, but when we draw an atom on something two-dimensional like this whiteboard or whatever, we usually use the Bohr model of the atom. Okay, so that's your nucleus here in the middle, your first energy level, second energy level, third energy level, and then corresponding electrons that go with the appropriate energy level. Okay, so there's your Bohr model. Okay, and the smaller orbitals, okay, smaller orbitals equals lower energy. Okay, so this orbital right here is your first level, and it has lower energy than this one right here, which is your third energy. Your third energy level. So the electrons in the third energy level are going to have a lot more energy than the ones in the first energy level. Okay? So let's go back and talk about that ground state versus that excited state. Let's look at something simple. Okay? Let's say that we've got an atom here with 3 electrons. Okay? Nothing fancy. All right? And when these electrons occupy this lowest energy state, all right, they are on this ground state. Okay, but when we add energy to this, okay, when we add energy, these electrons become excited. Okay, and mainly the valence electrons. The valence electrons are going to become excited, and when they become excited, they're able to jump to a higher, to an energy level that requires more energy to stay there. Okay? So once they make this jump, it becomes very, very unstable and immediately jumps back down to where it belongs, jumps back down to where it's most comfortable. Okay? But something has to happen to that energy. Okay? It gained all this energy to jump up here. Now it's losing it all and it's going back down. What happens to that energy? Well, that energy is emitted as light. Okay? It's emitted as light. Right? And depending on the wavelength of the light. Okay? So the wavelength of the light determines the color of the light. Right? 700 nanometers, if the wavelength is 700 nanometers, it's going to be red. Okay? If it's 400 nanometers, it's going to be violet. Okay? And anything in between, you're going to see all the colors of the rainbow. Right? This is called the visible spectrum. You may have heard that in biology, but that is the visible spectrum. Okay? Now, let's say that we have an electron right here, and it jumps to this third energy level, and then it jumps back down. Okay? That light is going to be different than light that is emitted when that same electron gets enough energy to jump 2 energy levels, and then has to go back down. Okay? These are different wavelengths because they're different energy amounts. Okay? Just like if something started on this third energy level and jumped to the the fourth energy level and then had to go back down. Okay? Let's say we had another energy level out here. The same electron gets enough energy to jump to and go back down. Again, these are going to be different wavelengths. Okay, and they're going to be different from these 2 wavelengths as well because they start out in different places and they end in different places. Okay, or they jump to different places. All right, so there's unlimited possibilities of the different shades of colors that you can get just based on the energies. And the most common example of what this is used for is fireworks. Okay, fireworks, they pack all this metal in and they shoot it up in the air and then it blows up. And when it blows up, it gets that energy. And those atoms, those electrons in those atoms, they gain energy. And then the light that you see as the firework is the energy being released from those electrons when they come back down to their ground state. Okay? That is quantum and photons.